All right, guys, so we're going to go ahead and talk about recursive rules. So a recursive rule just means that the rule that you're writing depends on the previous terms. So we are going to have arithmetic and we are going to have geometric recursive rules. So if you look at these formulas, remember that an arithmetic sequence was just when you were adding the same amount every single time. So this right here, this a sub n minus 1, this actually means the previous term. Okay, so that's the previous term plus the difference. So that's what an arithmetic rule is, right? If we had 2, and then we had 5, and then we had 8, and then we had 11, if that was my sequence, I just take my previous term and I add 3 to it. You can see that that common difference is 3. So to get the second term, I take the previous term, which is 2, and I add 3. To get the third term, I take the previous term, which is 5, and I add 3. So these formulas right here are kind of self-explanatory when you think about what an arithmetic pattern versus a geometric pattern is. So this D is just your common difference. That's not changing the definition of that. Right? Same thing for a geometric. So think about what a geometric pattern is. A geometric pattern is when you're multiplying by the same thing each time. So now I have my ratio. This is your common ratio multiplied by your previous term. That's all that's happening. So if we change this to be 2, and then 6, and then 18, and then 54, and so on, all you're doing now, we're multiplying by 3. So to get my second term, I take my first term, which is my previous term, and I multiply by that ratio of 3. To get my third term, I take my second term, which is the previous one, and I multiply by 3. So that's all a recursive rule means, is that you have to have the previous term in order to find the next term. And this is especially helpful with some of our non-arithmetic patterns. So when you have a recursive rule, I couldn't just tell you to find a sub 52. I couldn't tell you to find the 52nd term, and you couldn't just plug it in and find the 52nd term. You would have to find all the terms until you got to the 51st term to then find that next term of the 52nd one. All right, so our first example here is going to be just to write the first 4 terms of the sequence. So this is what a recursive rule looks like. They have to give you the starting term. They have to tell you where to start. Whereas if I gave you an arithmetic rule, you could plug in 1 and you would find the first term. You would know where to start. But there's a bunch of different sequences. Like this right here, this common difference is 3. There's a bunch of different sequences that exist in the world with a common difference of 3. 10, 13, 16, etc. -1, 2, 5, etc. So although we have some similar terms, it's an entirely different sequence. So because it's recursive, because we don't have an explicit formula, an actual rule like we've been working with, we have to give you that first term. So what this says is write the first 4 terms of the sequence. Hopefully you can see that this is an arithmetic pattern. Okay, because we're adding that 4 each time. So if my first term is 1, now my second term is going to be the previous term. It's going to be a sub 1 plus 4. So a sub 1 is 1. So 1 plus 4 equals 5. And then if I want my third term, it's going to be whatever my second term was plus 4. That's what this means. This a n minus 1, that means your previous term. So if my n is 3, my n minus 1 is 2. So I take that second term that I just got of 5, and now I do 5 plus 4. So my third term is 9. So my first term is 1, and then 5, and then 9. And then my fourth term would be taking my third term and adding 4 to it still. So my third term was 9, plus 4 is 13. So my pattern is going 1, 5, 9, 13. Those are my first 4 terms, and it's following that arithmetic pattern. All right, let's try example B. So again, same idea here, where I'm giving you that first term. I have to tell you where it starts. So you can hopefully see that this is going to be a geometric pattern. And it's geometric because I have 3 times my previous term. So if my first term is 1, then that means my second term is going to be 3 times my previous term. Well, I'm going to plug that in there. So 3 times 1 is 3. So then my third term is going to be 3 times my second term, or the previous ones. So 3 times, there's that previous term. So my third term is 9. And then finally, to get the fourth one, you take 3 times the previous term. So in this case, 3 times the third term, which is that 9. So you can see that because these follow the arithmetic and the geometric pattern, we can kind of write out our sequence like normal. Okay, those are going to be my first 4 terms. All right. So we're going to write a recursive rule for the sequence. So if we're writing a recursive rule for the sequence, that means it has to be a rule that is based on the previous term. So it doesn't matter if you have an arithmetic or a geometric pattern, or if you have one of those other sequences. If I'm writing a recursive rule, I have to go back and my formula has to include this n minus 1 as part of it. And I also have to include the first term. So maybe we write ourselves a little bit of a note there that you must include the starting term. And I'm going to put an S there in parentheses because sometimes you have to include more than just the first term. Something to look forward to. All right, so what we're trying to do here is we're trying to figure out what the pattern is. So we're going to look at this problem. Is this an arithmetic problem? Is it a geometric problem? Is it one of those other sequence problems? So you're just trying to find that pattern. So you can see here, hopefully, that you have an arithmetic pattern. And we have an arithmetic pattern because we're going to hopefully recognize that D equals 10. So if I want to write a recursive rule means for arithmetic, a sub n equals the previous term plus the common difference. So all I have to include is that common difference. So my rule is a sub n equals a sub n minus 1 plus 10. That's my rule. But we also have to include the starting piece. So this piece right here, that a sub 1, that's going to get me started. That's going to tell everyone that I want this sequence, 3, 13, 23. I don't want the sequence of 0, 10, 20, 30. I don't want the sequence of 5, 15, 25, 35. I want the sequence that starts at 3 and has a difference of 10. So I have to also include that a sub 1 equals 3. So there's 2 parts for this answer. And when you do this in Buzz, you're going to have to type in both of those parts. You have to include that first term. All right, so this is a recursive rule. This is a recursive rule because the rule right here depends on the previous term. So yeah, I could ask you for the 75th term, but you'd have to find the 74th term before you could add 10 to get the 75th. So that's where we do the explicit rule. So the explicit rule is just the regular rule, okay? The regular rule that you're used to. The regular rule. So because this is arithmetic, we can write a regular rule. We can use our a sub n equals a sub 1 plus n minus 1 times d. And remember, you only need 2 things to write a rule. You need your first term, which we have. We have that's 3. And we need our common difference. And our common difference is that 10 that we figured out. So if we want to write our regular rule, we're just going to do a sub n equals that first term plus n minus 1 times d. Can you leave your answer like this? Is this an A-OK way to write our answer? No. So you're going to have to distribute. You're going to have to get this into 3 plus 10n minus 10. So negative 7 plus 10n. That's going to be my rule. And make sure that we're including that a sub n. So we really try to understand the difference between the two. An explicit rule is your regular rule. That means that if I asked you for that 75th term, you could just plug in 75 and boom, you got it. As opposed to the recursive rule, relies on the previous term. If I asked you for the 75th term, you gotta go through and find all the first 74 of them. All right, let's try that with a geometric now. Spoiler alert. So here's my rule, okay, or not my rule, my sequence. So I want to still write that recursive rule. So I still have to figure out what the pattern is, whether it's arithmetic, geometric, or one of the others. Kind of already told you that this is geometric. So can you see why it's geometric? Can you see that pattern? Can you see that we are multiplying by 5/2? Okay, so multiplying by 5/2, we're going to go ahead and know that that's my ratio. Now thinking back to that original formula that we had for geometric, it's just your ratio times the previous term. So we've got the ratio. My rule is going to be a sub n, which is my ratio, times the previous term. So a sub n minus 1. That's my rule. I know. It's kind of simple. And then don't forget that you also have to include that first term. We have to include that we're starting our sequence here at 16. Because otherwise there's a ton of different rules that start any different number with a ratio of 5/2. So this is the recursive rule. It has the previous term included. So now if I want to change that to an explicit rule, now I'm thinking, okay, because it's geometric, I have to go back to that green paper. I have to know what a geometric is. So a sub n equals a sub 1 times r to the n minus 1. So you still only need your ratio and your first term to write the rule. So now we can just write it. We have them both, right? We have that first term is 16. We have that ratio is 5/2. So plug it in. So a1 is 16, and then my ratio is 5/2, and then exponent of n minus 1. Keep in mind, you don't have to simplify this. It's beautiful. Done. All right, that's it for video 1.